Let's set the midterm date so we have a concrete date. So I'm thinking take home, but I don't want to be presumptuous. How many want a take home exam, in class exam? Oh, wow. Okay. Unanimous vote. Amazing. All right. So be it. Take home, open book, open notes, but no Google searches during the exam. The exam is not an exam in Google searching. It's an exam of problem solving and insights and all that good stuff. So I'm thinking I'll make it available over a several day window. You can take it any time for 6 contiguous hours over a several multi-day window. So you can adjust the time that you take the exam according to your other schedules and commitments and other exams and responsibilities. So I think that's very flexible. So what if we make it available on the 17th, Friday the 17th of March, and have it all be due on say Wednesday the 22nd. So you have a 5-day window, and you can just pick some 6-hour contiguous time slot in that 5-day window and have fun with the exam, turn it in, end of story. Yeah. I'll make it available online as a PDF. It'll be like a link off the regular class website. It'll be trackable IP addresses, so we know who's gotten it when. Once you download it, print it out. Once you open it, look at it, the clock starts. So if you travel or if you're out of town, or you can just download it wherever it is you are for extra convenience. You don't have to physically pick up a hard copy. But do print it out, because when you turn in, you should turn in a hard copy, print it out, with all the answers spelled out and all that good stuff. So any other questions about that? And it'll cover everything we cover in class up to that week of March 16, I guess. So another 6 lectures or so worth of stuff. And mostly it'll be problem set 2, because problem set 1, I already gave you a lot of solutions, problem set 1, so I'm not going to ask you problems that I already gave you solutions for. That's just, I'm not going to insult your intelligence like that, right? So it's going to be mostly problem set 2, covering regular languages, finite automata, which we'll start covering more deeply today. Nathan already covered a couple lectures, but we'll pick up where he left off. Yeah. Yeah, so print out the PDF, wherever it is you happen to be, then write all the answers down neatly. Turn it in by sliding it under my door or giving it to Nathan, or one of those two. Or hand it to me if I happen to be there, or you can turn it in class if you happen to finish before a class lecture that week or whatever. Yeah. It'll cover the material up to that week, and if there's a problem in set 3 that is part of that material, I reserve the right to do that, but I can't imagine it'll be more than one problem from set 3, and only to the point that it pertains to the material covered up to that point in class. Namely, mostly regular languages, finite automata, closure properties. We're going to go through all that, very detailed. And if we get to context-free languages, there might be a thing or two about context-free languages, but proportional to our coverage. If we only get to context-free languages, say, on the Thursday the 9th, then it's only a week before the exam. Then I won't put a whole lot about context-free languages. I believe in fairness. I don't want to play gotcha with you. I don't think I ever do. All the problems you would have seen before, because they're going to come straight out of the problem set. So you have good couple, 2.5 weeks to still work on it in groups, solve lots of problems. Ideally, you should come to the exam, not be surprised at all, solve most of the problems on there, just write down the answers, walk away. End of story. It should be that easy. If you've been working all along and coming to the Monday night sessions and working in groups and solving problems, it should be a cinch. I don't have quotas. If everybody does well, everybody gets an A. Not just on the exam, in the course. If everybody aces everything, you can all get A's, I'll be happy. I don't feel like I need to give some B's and C's and D's and a few F's. It's just, if you're doing work, if you're studying, if you're learning, if you're diligent, more power to you. That's what we're here for. What else? Any other questions? Logistics? All right. So last time we talked about entropy. and Claude Shannon's information theory, which basically rules almost everything we do these days with computers, from compression to playing MP3s and MP4s and videos and talking to each other on a phone, sending messages. It all gets compressed, it all gets encoded, errors get detected and corrected, all according to information theory. That's sort of the masterpiece of transmission of data around, one way or another, in all forms. Very, very important. So there's a nice video on the web about Shannon and his contributions and why his work was so important, not just back then, but even today in everything we do. So for extra credit, watch this. It's like a 45-minute, or even, actually it's less, it's 30-minute, 29-minute kind of documentary, and you'll learn some interesting things about this guy. And there's Information Theory Society and Claude Shannon Award, and even to this day, he gets a lot of respect and homage. Here's that diagram here, right from his famous paper about information theory. And by the way, we're taking roll today, so sign your name when the roll sheet comes around. This information theory diagram from his original paper showing an information source and some encoder, a message getting through, gets encoded, gets then sent over some channel, gets received by transmitter, then gets decoded with some insertion of noise along the middle of the channel. How many remember that diagram? We showed that a couple lectures ago, or last lecture actually. So that's that diagram right there. That says a lot about communication and the issues around communication, and very importantly, the noise source and what to do about noise detection and correction. All right, Stephen Kleene, also a student of Alonzo Church along with Turing, invented recursive function theory, which basically means computability. It doesn't mean recursion in the call yourself kind of recursion, but means computable functions. And again, a pioneer of theoretical computer science. They were all at the Institute for Advanced Study in the 30s, the 40s, and he invented regular expressions, of which we're going to go very deeply into and prove some theorems about. And of course, the Kleene closure, the Kleene star, is named after him. And many other theorems as well. So Noam Chomsky is actually the first person on this long list of historical figures that I mentioned that's still alive. He's still at MIT, is probably pushing 90 by now, right? And basically, a lot of what we're going to study the rest of the course is based on his work back in the 50s and 60s. So he started as a linguist and basically pioneered linguistics and invented essentially modern linguistics. He put them on a formal footing. Before that, it was all kind of fuzzy and squishy, and then he basically put it on a mathematical, logical, notational footing, and that was a huge leap forward and opened up a whole bunch of sub-areas, including formal languages, which we've been studying so far quite a bit, and we'll study it even more for the rest of the course. He invented context-free grammars on which compilers are based and many other things are based. The idea was to try to figure out natural language, human natural language, spoken language, whether it's English, Chinese, or Hindi, or whatever, French, German, Russian. He looked for rules to construct sentences and rules of grammar to construct grammatically correct phrases and sentences and try to automatically denote what's grammatically correct and what's not grammatically correct based on what the grammar's rules can generate or cannot generate. This Chomsky hierarchy we've seen before, regular languages, properly contained in context-free languages, and so on. This is a Venn diagram. We're going to study the heck out of this diagram and all of its nuances and relationships among these classes and sets and subsets. We've already done a little bit of that. We already looked at decidable languages, for example. Indirectly, when we said the halting problem is not decidable, that means it's not in this Venn diagram oval of decidable languages. It's somewhere other than that. It's actually in this oval here. There it is, the H. H is the halting problem. The inverse of the halting problem is not even recognizable. We'll get to that. We'll prove that. It's all due to Chomsky and, of course, Turing. So Chomsky took what Turing did and kept refining this dichotomy among languages, their containments and non-containments, and all these striations along this Chomsky, so-called Chomsky hierarchy. And this diagram can be expanded a great deal. I'm just showing you a little bit of the main core of it. just half a dozen or so sets here, but you can extend it to literally hundreds of sets, and really you can extend it to infinite number of sets. But hundreds of them have names, actually. Hundreds of them are so important that we actually name them, and we know what they are when we call them by name. Influenced psychology and cognitive psychology in particular, philosophy of language. So things are named after him: Chomskyan linguistics or Chomskyan syntax, Chomskyan models. It's interesting that he's the #1 most cited human being alive in terms of citations to his work, references by other works. He's cited literally millions of times, maybe tens of millions of times, all over all the other fields. So he's cited more than any living person. If you include dead people on that list, he's like #7 in human history. And that list, if you include dead people, includes Plato, Socrates, Aristotle, and Jesus Christ. So he's very, very well cited, amazingly. And he's still around and doing work. And lately, the last couple of decades, he's been getting to be kind of a critic of U.S. foreign policy. And of course, now it's not that hard to do that. Here are some of the books that he wrote. He wrote dozens and dozens of them. But originally, the serious stuff about syntactics, structures, formal languages, the Chomsky hierarchy was late 50s, early 60s. But then he started writing about politics and failed states and the Kennedy administration back in the 60s, about hegemony, basically American so-called imperialism, how he sees it, and lots of books on lots of topics. Actually, that book about hegemony by Noam Chomsky was held by Hugo Chavez of Venezuela. He got up in the United Nations and gave this fiery speech thumping Noam Chomsky's book, while he was talking, and that's the book right there. Of course, which made it a bestseller immediately, because all the media outlets just went out and tried to get it. And then, of course, he visited Venezuela. Here he is with Ali G, of Borat fame later on. He was a good sport about it. There are fist bumping. Some people weren't so good sports about it. So that's sort of what he's been doing lately, just so you know. So if you can only watch one movie or documentary about him, probably this one is a good one, Manufacturing Consent, How the Media Affects Everything That Happens. He wrote this back in the 80s. Of course, lately, in the last year or so, 2 years, we saw this on steroids, that the media can affect, for better or worse, not just what people think, but what happens in the world. Well, this business about fake news, he was basically talking about it 30 years ago, before the term was even invented, but the phenomena was still there. It was just more subtle back then. Now it's much more in your face. So Don Knuth once said about Chomsky, he said, I must admit to taking a copy of Noam Chomsky's Syntactic Structures, that's that book that we just saw, along with me on my honeymoon in 1961. Here was a marvelous thing, a mathematical study of language in which I could use as a computer programmer's intuition. So Don Knuth considered Noam Chomsky his hero and based a lot of his own work on Chomsky's ideas and discoveries. I'm not sure how Mrs. Knuth felt about her husband bringing that book along to the honeymoon, but still, this is one of the many points of impact that Noam Chomsky's work had. The funny cartoon on the web, The Adventures of Noam Chomsky and His Dog Predicate. Your mileage may vary, but I just thought I'd throw it on there. You can look at it at your leisure offline. And not everything he says is without controversy. In fact, a lot of his stuff that he said lately about politics is highly controversial. And even in linguistics, there are people who disagree with his notion of how the mind wraps itself around grammars and how languages are generated and evolve and become a phenomena in thinking beings such as us. So, some people question what he says and others are not so subtle about it. So just so you know, there's some controversy along with, a lot of admiration. Okay, so now we're going to switch gears. So we're sort of done with the historical stuff. Long arc, beginning with ancient Greece, leading up to present, how things got connected, who influenced who, how we got to this point. And now we're going to start digging deeper into the weeds of the Chomsky hierarchy, formal languages, starting with regular languages and up the hierarchy into context-free languages, decidable, undecidable languages. We've already seen examples of some of these. So as far as the book goes, we're going to go back to chapter 0 for some of the notation and introduction. So make sure, I'm sure most of you have read that already, but in case you haven't, go back and look at the mathematical underpinnings. What is a set? What is a sequence? What is an element? What is union? What is intersection? And so on. There's also a handout on the website that's about a dozen pages long that lists all these definitions in one fell swoop, in one-stop shop for all these definitions. So that's sort of, if you don't get a definition or you want to refresh yourself on a definition, just go to either chapter 0 in the book or that handout on the web, class website, or both. So formal languages. First, we start with an alphabet. It's a finite set of symbols, such as A, comma, B. So A and B are both symbols. Sigma is the collection A, comma, B. It's a set. I know that Nathan covered some of this stuff a few lectures ago, so we're going to kind of breeze through it until we get to a point that hasn't been covered yet, and then we're going to slow down a bit and dig deeper. So a string is a finite sequence of symbols, not a set of sequence, because order matters, like A, B, and so on. A language could be possibly an infinite, but could be a finite set of strings. So here's a language that's, in terms of regular languages or regular expressions, this is A star, or more precisely A plus, say. The length of a string is simply how many characters are in it, how many symbols long is it. The empty string is the string that has no characters at all in it. It's the unique string, just quote, quote, or quote, unquote. It's just the string of length 0. It's the unique string that has that length. There's no other string that has that length other than the empty string. String concatenation is simply the juxtaposition of all the characters of one string with the characters of another string side by side, and order matters because W1, W2 is not the same as W2, W1. It's not commutative, but it is associative. Language concatenation is an extension of string concatenation to entire languages. So if you wanted to concatenate two languages, which are sets of strings, what you better do is concatenate all possible strings pairwise, the first coming from the first language, the second coming from the second language, in all possible combinations. Take these pairwise concatenations, throw them into one bigger set, and that's your concatenation of the two languages. How many get all this? Okay. Any questions? Stop me right away if there's questions, because I'm sort of going quickly through this, thinking you've either seen this before, read this before, or remember Nathan's lecture from a few weeks ago. Either way, you're good. String exponentiation is simply repeated concatenation. So W to the K is the string W concatenated to itself K times. Just like 5 to the 7th in arithmetic is 5 multiplied by itself 7 times. So it's the extension of exponentiation operator to strings, not just numbers. And these green ones are examples of each. By the way, the empty string is a unique string that concatenated to anything on the left or the right gives you that string right back. So it's the identity element with respect to concatenation, the empty string. So now you can exponentiate languages by concatenating it with itself K times, extending the language concatenation operator to arbitrary number of times. So the language 01 concatenated with itself 32 times is all 32-bit strings, all 32 long bit strings. So there's 2 to 32 different strings, 4 billion roughly, different strings, each of size 32 bits. More definitions. The reversal of a string is simply all the characters written backwards. Straightforward. Now you can extend the reversal of a string to reversal of languages, which is the reversal of all of its strings. So to reverse a language, you operate individually. Each string, reverse each string separately, uniting them all together, and you got the reversal of the language. So notice how operators are built on other operators very heavily. First, you define an operator on strings, and from which you can extend that to a similar operator on languages, and then you can even do that for entire classes of languages, and so on and so on. Union. The union of two languages is simply the set union. So something is in the union if it's in one or the other, or in both. That's okay too. Here's an example of a union. Two languages give you this language. Language intersection is, again, what you'd guess, just the intersection of the two sets. Remember, a language is a set, after all. Language is not a sequence. A language is not an animal, mineral, vegetable. It's a set by type. So once you have sets, you can take intersections and unions, and that's what happens when you do. And you can take the difference of two sets, or two languages, because languages are sets, so the types work out. And the difference between two languages is everything that's in the first but not in the second. And of course, union and intersection are commutative. Difference is not. How many get all this? Okay, it's only a third of the class raising your hand. So you want to ask questions? Or maybe I'll ask again, how many understand all these definitions? Okay, that's better. You got me worried there for a second. Okay, you're good now. Clean closure now can be defined in terms of these previous operators. So the clean closure, L star, is simply all powers of the language L union together, all of them, infinite number. So it's L to the 0, union L to the 1, union L to the 2, and so on, all the way out. Okay? And that big union of all these things is the clean closure. The clean plus, L plus, is similar to the clean closure, except the first term is missing. You don't have an L to the 0 there. You don't have an explicit empty language. Remember what L to the 0 is? The language containing the empty string, the trivial language. Not the empty language, the trivial language, the language containing the empty string. So now we have clean closure and we have clean plus, or L plus. And now when you say sigma plus, or excuse me, sigma star, you can also say sigma plus without the epsilon, but if you say sigma star, it's all powers of sigma, all union together, which really means all strings over the alphabet sigma, and by all strings I mean every last possible string that you can form from the alphabet characters is in that set, all of them, all possibilities. Right? Now, here's the first theorem that we're proving, we'll prove many others. Here's the first one we're proving on these definitions, that sigma star contains no infinite strings. Anybody want to prove that? How would you prove that sigma star, defined like this right here, has no infinite strings in it? It has an infinite number of strings, but not a string that is in itself infinite. Because it does have an infinite number of terms. Sigma star is equal to sigma to the 0, union sigma to the 1, union sigma to the 2, union sigma to the 3, and you go all the way out, never stopping. So why aren't there any infinite strings in sigma star? What's a short reason for that? Yeah. So, for example, this term here, L squared, you're saying it's countably infinite. Yeah. Okay. Yeah. So each term in this sigma star, sigma squared, sigma cubed, has a finite length strings in that term. Like all strings of size 1, all strings of size 2, all strings of size 3. And it does go all the way out. But there's no infinite strings because any term has only finite length strings of higher and higher lengths, but only finite length strings. So you never get to an infinite string from the first term, the second term, the third term, the Googleplex term, or any other term. So there's no infinite length strings coming out of any of the terms, which means it ain't going to be in their union. Just like my right shoe is not going to be in the union either, because it's not in the first, it's not in the second, it's not in the third. So it ain't going to be in the union. It's not going to magically appear in the union if it doesn't appear in any one of the components that we're unioning them together. How many get that? Very important. So I say that up front and very explicitly because, before I used to say it very explicitly, some people would go for weeks and even months and most of the course thinking that sigma star contains infinite strings, and it does not. Absolutely doesn't. Questions about that? All right. Yeah, question. So, by definition, an alphabet is a finite. That's why I put the finite in red, because I knew you were going to ask that. Somebody always asks that. Any other questions? Now, you can separately define an infinite number of symbols and work, but for our purposes and in this class, sigma is a finite set. Good question. All right. Let's keep going. So language complementation. So L bar or L prime, however you want to denote it, is the negation of the language with respect to sigma star. So L bar, the negation of the language, or L prime, however, different ways to denote it. You can say L naught is whatever is in sigma star minus L. In other words, it's everything that's not in L. Because sigma star is everything. L is some stuff. So L, sigma star minus L is everything that's not in L. It's the negation of L. Now, you have to be careful what you're negating it with respect to. You can't say it's everything in the universe other than what's in L. Because everything in the universe contains also my right shoe and your car. So L prime or L bar will not contain my right shoe and will not contain your car. It'll contain stuff in sigma star that's not in L. Not stuff all over the universe that's not in L, including weird things like cars and shoes. Very important. I know it sounds silly when I say it right now, but sometimes people forget what they're complementing with respect to. Some large universal set, not the entire universe whatsoever. Okay, here's another theorem. L star star is the same as L star always. So starring it twice doesn't do you any good. Starring it once already gets you there to starring it any number of times. To prove something like this, I'm not going to give you the proof here, but for extra credit, prove it. And one way to prove equalities like this is prove that the right-hand side is a subset of the left-hand side, and separately prove the second theorem that the left-hand side is a subset of the right-hand side. So prove that the right-hand side is a subset of the left is a subset of the right, and if two things are each a subset of another, the two are one and the same. How many understand that strategy? Good. So sometimes that's easier to prove these two separate lemmas than the actual theorem of equality to begin with. Okay, so use this strategy here to try to prove this theorem. It's just a paragraph of a few sentences. It's not a big proof, but also prove that L plus is L concatenated to L star, always, no matter what L is. That's an identity, it's a theorem. The trivial language, I think we mentioned before, is a language containing the empty string, and that's the identity element with respect to language concatenation. The identity element with respect to string concatenation, not language concatenation, but string concatenation identity element is simply epsilon, the empty string. But the identity element with respect to language concatenation is the set containing the empty string. And by the way, the empty string is not the same as the set containing the empty string. There's two different things, because the empty string is a string. The set containing the empty string is a language or a set. A set cannot be equal to a string. Just like the set containing your car is not equal to your car, because one of them is a car and the other one is not a car. It's a set that happen to contain a car, but that's irrelevant. The types differ. If the types of two things are different, the two things cannot possibly be equal. How many understand that? So that's a litmus test for equality. It's not necessarily saying that if the types are the same, the objects are the same, because 5 is not the same as 7. But the string 5 is not the same as the number 5, because one is a number and one ain't a number, is a string. Very important to remember that. I know it sounds silly and obvious and trivial when I just say it like that, but most of you will make type errors throughout the rest of the course. Hopefully not too many. You'll equate or not equate things that have different types and won't even notice that you're dealing with the wrong type all of a sudden. If you don't know the type of something, you have no idea what its value is. Okay? If you don't know that it's a mammal, you have no way of knowing it's a zebra. Right? So think about types when you're dealing with objects, you're trying to find equality or lack of equality or relationships among them. First, nail down the types. Know what type of objects you're dealing with. Never mind the value of these objects. Right? Very important, and we'll get back to that. Whenever I hear a type error, I'll point it out and I'll remember this discussion here. If two things have different types, they can't be the same object. All right, the empty language is a unique language that contains no strings. It's the empty language. It's the empty set, in fact. And we already mentioned that sigma star is countable, or if we didn't mention it, we're mentioning it now, and the simple reason is dovetailing. You can list sigma star by string length, list all the strings in sigma star of length 0, then of length 1, of length 2, of length 3. There's only a finite number of strings of length 3, of length 4, of length 5. List them all out, number them all the way down. That's dovetailing, which means Z star is countable. It's infinite, but it's countably infinite. It's not uncountably infinite. How many get that? Dovetailing. Any questions about that? It's very important because this will come up again and again. On the other hand, 2 to the sigma star is not countable. What's 2 to the sigma star, by the way? What's 2 to the p? If p is a set, what's 2 to the p? Never mind sigma star, but any set, p. P is a set. What's 2 to the p mean, notationally? Power set. What's the power set? With a longer sentence explanation. Good, a set of all subsets. So 2 to the sigma star, now p is sigma star. Sigma star is all possible strings. So 2 to the sigma star is a set of all subsets of all possible strings, meaning the set of all languages. So it's a set of sets. So sigma star is a set of strings. A string is a sequence of symbols. A symbol is an element from an alphabet. So sigma star is a set of strings. It's a language, in other words. 2 to the sigma star is a set of sets of strings. So sets are nested too deep. There's braces, and then inside lots of other pairs of braces, each one being a language, many of which are infinite, some of which are finite. How many get the type of 2 to the sigma star? It's a set of sets. And if you want to spell out the entire type, it's not just a set of sets. It's a set of sequences of symbols. The type is compound 4 deep. Symbols, sequences, sets, and sets of sets. So again, sigma star, its type is fully spelled out. A set of sets of sequences of symbols. Type compounded 4 deep. And things will get even more esoteric than that later on. So keep your mind wrapped around very tightly around the types of objects. Don't let them get away from you. Because if the type gets away from you, everything else will follow very quickly away from you too. Again, if you don't know the type of something, you don't know that something. Think about it. All right. So pretty much we've covered chapter 0 in just a few minutes. Presumably a lot of this was seen by you in discrete math or elsewhere or before, or it's just common sense. But now we're going to get into the regular languages very heavily. We're going to breeze through what Nathan already covered and then kind of slow down when we get to the new stuff. So finite automata, we're going to define that as a 5-tuple and so on. So now we're on page 31, 32, 34, 35, chapter 1 of the book. We'll quickly breeze through that and then slow down when we get to something new. So a finite automata is a machine that changes states while processing symbols, and it processes the symbols one at a time and keeps changing states as it does so. So it's simply the quintuple. The set of states is the first element or component of a finite automata. So it's a finite set of states like Q0, Q1, Q2. You can call them whatever you'd like, right? These states. And you can draw them like using ovals, like a graph notation. And transitions, you can use arrows like edges in the graph, directed edges to denote transitions. So you have a transition function that says if you're in one state and you see a particular symbol, you jump to another corresponding state based on the first state and the symbol that you saw. So the function takes you from a domain of states crossed with symbols to more states. Okay? The initial state is some unique state, Q0. You can call it whatever you'd like. Typically, we put a double circle, you put a little caret into it, and that denotes that it's the unique start state. It's where the machine starts if you fire it up before it does anything else. It starts on that state. And final states are states where the machine ends or terminates, and those are usually denoted by double circles notationally, visually, graphically. Of course, you can just focus on the algebraic notation here, but it behooves us to kind of look at the picture, because the picture is worth 1,000 words, or at least a few hundred words, when it comes to denoting things. We're very visual creatures. We have a huge cerebral cortex, a visual cortex inside there that does a lot of pre-processing. So pictures are usually more informative than just algebraic symbols. Of course, your mileage may vary. If you're a very, very algebraic person and pictures don't do anything for you, okay, that's okay too. Then focus on the notation instead. So the finite automata is simply all of these things juxtaposed together as a sequence. It's the set of states, Q, the alphabet, sigma. Remember, that's a finite alphabet. The transition function that tells you what happens when you're in a certain state and you see a certain symbol in the input. What do? You go to another state, and that's a transition function, delta, for change. And then, of course, you got to start somewhere, Q0. You got to finish elsewhere, F. F is a set of states. You must start in a unique place, but you can finish many other places. Just like in your program. In your program, you have a single, unique first statement that the program starts at. Not 12 different places the program can start at. It starts only one unique single place. The program, though, can end in many places. Many places you can have an end or a quit or a break or whatever that terminates the program. There could be many of those. There could be many endings, but only one beginning. So that's why Q is an element, but F is a subset of all possible states. How many get this? Good. Any questions? So far, we basically defined finite automata. Here's an example. Finite automata that accepts all odd-length strings of zeros. You start here in the initial state, purple, 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 color-coded. If you see a 0, you go to this final state, Q1. If you see another 0, you go back to here, see another 0. So every even number of zeros, you'll end in this state, Q0. Every odd number of zeros, you'll end in this state, Q1. And only Q1 is final, red, final, red. So you'll only terminate if you run out of input when you've seen an odd number of zeros, which means this machine will accept only odd-length strings of zeros. And sigma is just a 0. There's no 1 even. It's a very simple machine. I'm not saying it does much. It basically does parity, counts parity of strings of zeros, odd or even. So the definition of acceptance, basically implicitly here, is if you exhaust the input to your finite automata and you end up in a final state, you accept. Otherwise, you reject. And notationally, this diagram, this finite automata looks like this. Right? Q0, Q1 are the two states. 0 is the sigma, the alphabet. Not a whole lot to it, just one character. The transition function is probably the most complex, if you can call it that. Here it's pretty simple even. The most complex part of any finite automata tells you which state you're in and which symbol you must see to get to this other state that's paired up with that first pair. Okay, so notationally, you have ordered pairs, each one of which is an ordered pair internally, comma, a state. So that matches the notion that the domain is Q cross sigma, state and a symbol, and the range is just a state. Right, so keep in mind the types of objects we're talking about. So again, we already mentioned this, but here it is spelled out. The finite automata consumes one string at a time while changing states. It accepts if and only if it ends up in a final state when the input is exhausted. Rejection is anything else. Notice I'm not saying it shouldn't be in a final state, but should be in a non-final state for rejection. I'm not saying that. I'm saying it's anything except the first definition of acceptance. Why? Because sometimes the machine can crash. Sometimes it's in a state and it has nowhere to go. That too is rejection. Okay. So if the machine hangs because it has nothing to do at that point, no place to go, no definition in the transition function that tells it what to do, that's not an acceptance, and by definition it's a rejection. All right, so here's a machine that accepts all strings of form AB, 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 in other words, AB quantity star, in terms of regular expression. You see an A, you go to this other state, you see a B, you go back to the initial state, AB, AB. So as long as you see AB, 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 you're good because you end up in an initial state, which is also a final state. That's okay. An initial state can be also a final state. Nobody said that the initial state should be disjoint from the set of final states. It could be an element of them. That's okay. And here's a complete description in terms of notation, in terms of the algebraic notation of this machine. So this machine will accept all strings of the form AB, AB, AB. Any questions about that? How many understand that perfectly? All right. So, but notice something strange happens. If you're in state Q0 and you see a B, you have nowhere to go. If you see an A, you go here, according to this arc. But if you see a B in state Q0, there's no outgoing arc with a B in it, so the machine will crash right there and then. It will abort, not go anywhere, not do anything, but certainly not accept. So that's an implicit rejection. So there's a solution to converting implicit rejections into explicit rejections and make the machine deliberately and explicitly reject if it doesn't have a well-defined transition. And what you do is you create some sort of a kind of a garbage state, a dead-end cul-de-sac state, that every time where there was an implicit rejection, like here on a B or here on an A, you take the A or the B into this garbage state, and there you stay in that state forever for the rest of the input. And that's not an accepting state. It's a non-accepting state. It's not in F. And once you're in here, there's no way to escape from it back to the main body of the machine that was defined previously. And that's an explicit rejection now, as opposed to an implicit rejection. So now this machine always has somewhere to go. And it always does the right thing in terms of its language being the same as that of the original machine without this added state here, without the Q2. How many understand that? Good. It's like in your program is covering all bases. When you have a big case statement, you don't leave anything hanging. All the exceptions are spelled out explicitly, including, if you must, use an else at the end, that all else conditions will fall into some other bucket. But you don't leave anything hanging. Right? So it's like spelling out the if, then else in your code, or if it's a case statement, all the possible cases, including all the remaining ones besides the ones that were spelled out earlier, like a big else at the end of the case, whatever. That's sort of what we're doing here. All right, the transition function notationally extends from symbols to strings. You can say delta, which is defined as Q cross sigma, you can now define it as Q cross sigma star. In other words, it takes you from a state and a string to another state. So you extend the definition of delta from a single character to a sequence of characters, arbitrary sequence of characters, including no characters at all, which means you stay in place, you don't change your state. And that's simply the recursive definition. So if you go from some state Q0 based on a string W followed by a character X, it's the same as if first you process the W, and then after that, you take that final jump character X. And the types all match up in a domain, the ranges are all match up in terms of types, everything is consistent. And that's just an extension of a transition function from symbols to strings. Right? And the language is regular. Here's kind of the big definition. A language is said to be regular if and only if it's accepted by some finite automata. I don't care which one. As long as there exists a finite automata that accepts a particular language, that language is now said to be regular. It's defined to be regular. It's an if and only if. Okay, so that's the definition of a regular language. There's some finite automata that does that job. What job? Accept that language and nothing else. All right, here's another theorem. If you complement a regular language, you get a regular language back. Not the same one, it'd be a different regular language, but it'd be a regular language nevertheless. It won't be some other type of language that happens to be not regular by some fluke. So that what we're saying is the complementation operator preserves regularity. So one easy way to look at it is you take the machine that does whatever job you want, whatever language you're accepting, and basically you take the final and non-final states and negate them. You make every state that was final, you make it non-final, and every state that was non-final, you make those final. And so that machine, a new machine, looks like this. It's a complemented machine. This state Q0 was final in the original machine. It's non-final in the new machine, the complement machine. These two states, Q1, Q0, were non-final. In the final, in the complement machine, they become final. So you just flip the final and non-final states, which means the machine now does the opposite. Whatever the machine accepted before, now it accepts everything else and not those things. How many get that? Good. So it's pretty straightforward. In other words, you simulate the old machine and do the opposite in some sense. That's what this construction is. Okay. And here I explicitly wrote as a regular expression the complement of this AB star language. This is the machine we had from the previous slide, accepting AB, AB, or AB star. This is the regular expression that denotes the complement of that. Basically, it's anything that either starts with a B, which AB star ain't, or ends with an A, again, which is not that, or has an AA or a BB in it somewhere. And those three cases cover all bases. That's what AB quantity star complemented is in terms of regular expressions. Now, we haven't formally defined regular expressions, but soon enough we will, probably by next lecture. Probably won't get to it today, probably by next lecture. But most of you have seen regular expressions before, so I'm kind of relying on your intuition. How many have seen regular expressions before? Good. You see them all over the place, right? When you program, when you run compiler, when you run grep on Unix and look at search for regular expressions or whatever. They appear all over the place. But we'll define them very, very formally. Okay. At some point soon. All right. So an exercise, define a finite automata, and D means deterministic, because soon we'll talk about non-determinism too. Define a deterministic finite automata that accepts all strings over AB where any A precedes any B. So it can have lots of A's and B's, but if you have a A, it must precede any B. In other words, you can't have B's before A's. So sure enough, you can have as many A's as you want, right? And then once you see a B, you can have as many B's as you want, and you're still good. But if you ever see an A after a B, you end up in this garbage cul-de-sac dead-end state, and from there, there's no escape. You just keep cycling here, and it's not an accepting state. So more and more characters in input will not get you into any accepting situation. So basically, it says any A's must precede any B's in any combination. You can have no B's at all, in which case you just have a bunch of A's. That's okay, too. That means there's no B's that preceded A's because there are no B's altogether. All right? So in terms of regular expressions, it's A star, B star. That's what the language of this finite automata is. It's denoted by the regular expression A star, B star. And you can ask yourself, what's a complement of L? Right? And you can start writing the complement as some B preceding some A. And here you have sigma star, sigma star, sigma star garbage states. Once you do that, you can see that you don't have to have a lot of B's preceding an A. You can have one B preceding an A and not even more A's than that. So as long as there's one B preceding some A with some junk in the middle, and you can have junk on either side, you're in the complement. You're not in the original language A star, B star. So now we're computing the complement, and we're simplifying it. So these are simpler and simpler, shorter regular expressions that still denote the exact same language. It's just more concise. They're shorter. Right? So we can have a lot of B's preceding an A, and in fact, suffice to have a single B preceding a single A, because if you have a lot of B's preceding an A, eventually one of them, the last one of them, will precede the A, and that's already a no-no for membership in the original language. And once you do that, you realize that you can simplify it even further. You can look at the first B that precedes, the first run of B's that precedes an A, and there it is. And you can have some A's before that and anything you want after that. And that's still a no-no, and so you're part of the complement. Anyway, it takes a little bit of thinking or getting used to minimizing regular expressions. It's not easy. Minimizing regular expressions actually is a tough problem in general. But here's an example where we minimize it nicely until it became much shorter than the original, and all these are equal to each other in terms of the languages that they denote. Now let me ask you a type question. Is A star, B star a regular language? How many say yes? How many say no? How many understand the question? Okay. So I'll ask again now if you've had 10 seconds to think about it. Is A star, B star a regular language? How many say yes? How many say no? And remember, I said this is going to be a type question, a type-based question. So we're talking about types here. So is A star, B star a regular language? Somebody catch the type error in that statement. You could if that symbol, but what is the type of A star, B star? It's a string. A star, B star is an A followed by an asterisk symbol, followed by a B, followed by an asterisk symbol. It's a regular expression. A regular expression is not a language. A regular expression can denote a language, but it isn't the language itself. I told you there'll be type errors, so I just, on purpose, caused most of you to stumble over a type. Now you're getting it. Don't confuse types. So if I say, I am Gabriel, I just made a type error. Where's the type error in that statement? Yeah. I'm a human being. I'm not a string. So I lied. What I said was not correct. I'm not Gabriel, quote unquote. I'm a human being whose name can be referred to as Gabriel. But my name is not me. My name is a separate object that's a string. I'm not a string. Not the last time I looked. So again, type errors are subtle. And sometimes we gloss right through them in real life. So you say, hi, I'm John, I'm Jane. Yeah, nobody's going to stop you and just have this discussion with you unless they want to make a jerk of themselves at a cocktail party. You say, no, you're not John. You're a human being whose name is the string, quote, John, unquote. But that's much more precise. Now, in this class, this matters a lot. In real life, people know what you mean and can gloss over it. How many get all this? And the reason I'm harping on this, again, because I guarantee you that most of them will make this error over and over again throughout this course when the stakes are much higher than this. We'll come back to that. Okay, so for extra credit, play with this tool on the web, download it, create finite automata with it's called JFlap. It's a nice workbench that allows you to create finite automata of all types. Extra credit, this is one of the required things because this will help you a lot constructing finite automata, playing with them, run them on different strings, see if they accept, reject, modify them, debug them, run them again, and so on and so on. So it's like a programming workbench for finite automata. And it has a very nice user interface. It's graphical. You can create these states graphically like nodes in a graph. You can draw these edges using a graphical draw tool, and you can move these nodes around and lay it out in a nice, elegant configuration, and write it on different strings, and so on and so on. You can even create non-deterministic ones. You can even create grammars. You can create Turing machines. There's a lot more in this tool than just finite automata in regular languages, but it's a good start. So get used to playing with this tool. Work it. Get used to it. Debug your finite automata with it. Run them. Otherwise, you'd have to do it by hand. It's like coding by hand without a compiler. Yeah, you can write all the code down and simulate it by hand, line by line, but that's nowhere near as efficient or fun as sending it to a compiler and then running it and seeing what happens, very quickly. So same idea. So don't just play with finite automata by hand. Test them, benchmark them, run them, see how they behave, modify them if necessary, debug them if you must, and so on. There's some more screenshots from this tool. You can also do push-down automata. We'll get to those pretty soon. A couple of lectures. You can also do Turing machines. You can do grammars. You can convert machines to grammars and grammars to machines. And it's a very powerful, kind of robust tool. It's pretty evolved. It's been around for many years. So extra credit, play with that. It'll be to your benefit. Okay. It's like having a compiler as opposed to running code by hand, one line at a time, while you scratch your head. Not very efficient. This is a lot more fun. All right, so let's talk about regular operators. Now we're pages 44, 45 of the book, section 1.1, 1.2. So we're going to define some theorems about what certain operators do to regular languages, what they don't do to regular languages. So the intersection of two regular languages is necessarily a regular language too. In other words, intersection, the operator of intersection preserves regularity. Just like the operator of addition preserves being an integer. So if you have two integers, their sum is an integer. The division operator does not preserve integer, because 1/2, they're both integers, but 1/2 is not an integer. It's a fraction. It's a quotient. So why is it that you have two regular languages, you intersect them together, you get a regular language back necessarily every time? Why can't you not sometimes not get a regular language back? Well, there's several ways to prove it, but here's an easy way to see it. It's a sort of so-called parallel simulation. So what you do is you simulate on the same input string two different finite automata. So this is the execution trace of the first finite automata. Here's the execution trace of the second finite automata on the same input string, like AB, AB, whatever. Now these two finite automata are separate and different from one another, but each one starts at its own start state and changes states as it goes, because it's deterministic, and that's what finite automata do. They change states based on what symbols they see. Okay. But now we're going to combine these two finite automata into a single one. So this is a complete execution trace, and because the input symbol, the input string had 1, 2, 3, 4, 5, 6, 7, 8 different characters, they both have execution traces of size 8, because they're both deterministic and they both do their own thing separately from the other, but they both do 8 steps for the 8 symbols of the input. Question? Yeah, so we'll get to that in a second. So hold on for about 2 minutes on that. So what we're going to do is we're going to create these super states. Each super state of this super machine, this combined or cross product machine, is a combination of two states, one from the first, one from the second. So we have all possible combinations of pairs of states, one from the first machine, one from the second machine, taken in all possible pairs. Each one of those becomes a larger green blob, or I call them super states to distinguish them from the original small or original states. And now what you do, instead of having this state going to that state and this state going to this state, I'm going to have this, take it one step at a time, I'm going to have this superstate here going to this superstate and this superstate going to that superstate. So a superstate goes to another superstate using this super transition in blue if and only if, component-wise, the first substate of the first superstate goes to the first substate of the second superstate, and the second substate here goes to the second substate there. And if both of these little transitions fire and get you to these two different places, this big pair of states as a superstate gets you in one super transition to this second pair of states being a second superstate. In other words, I'm simulating these two machines in parallel, pairwise, in lockstep, one transition at a time, one for each. And if one of the two machines accepts in one of its states, I'm going to make that whole superstate be accepting. Why? Because it's the intersection of two languages. So if one accepts or the other accepts, or if both accept, the whole thing has to accept. Suffice it for one of the two components to accept, that's good enough, you got to accept. You don't care if the other one rejects, because one accepts. Oh, wait, excuse me. Oh, that's the union. I just described the union. Okay, which just implicitly proved that the union preserves regularity. But for intersection, both must accept for the state to accept. Were you going to catch that? Good. Means you're understanding what's going on. Sometimes confusion is a good sign. So both must accept, and you accept, and you're good. So which means this superstate here must be a final state in this super or hybrid construction. Okay? So the initial state is still where both are initial. So the purple initial superstate is where both of them were initial state, one per machine respectively. And the final states are where both accept. This one right here, for example. And these two, not so much. Not unless you were doing the union, which we're about to do in a minute. Okay, so what have we done? We created this larger machine. It's still a finite automata, but its states are pairs of states of the original machine. Still a finite number, but they're product of the two sizes of these two original state sets. And the resulting super machine here accepts the intersection of the two languages accepted by the original two machines. Right? So in terms of algebra, if you want to see the notation, if this is the first machine, Q1, delta 1, Q prime, F1, this is the final set of states of the first machine, and so on. Here's the second machine. The combined machine has its own superstates be the cross product of the two state sets Q1, Q2. The cross product means all pairs in all possible combinations. The cross product is every element from the first, every element from the second, taken as a pair in all possible ways. So this whole thing is called the cross product construction, therefore, because you're crossing the two machines together. You're bashing them together in a way that simulates them both simultaneously in parallel, and you still get a bigger finite automata. Not the same as the original two, but the one that does what both do simultaneously so that you can compute the intersection. And therefore, the intersection of two languages is irregular languages, because here we just created a finite automata that accepts the intersection, which makes the intersection regular. Remember what the definition of regular is. If there is a finite automata that accepts it, it's regular. So that's what it is notationally, that's what it is diagrammatically, and that's the explanation. So to change from a superstate to another superstate, you apply the transition function originally of the first machine on the first component with the same input character x, and separately the transition function of the second machine, you apply it on the second component of the superstate q sub j with the same input symbol x in both cases, and that transitions you into the new superstate, the new superstate. How many get all this? At least conceptually. Okay. But it was only half the class, so ask me some questions if you must. In fact, I'd like you to ask me questions so we can clear up any misunderstandings before we move on to more complicated things. So this is the first non-trivial theorem we've seen about finite automata. We'll see much more complicated theorems than this. Yeah. Yes, it'll be the set intersection. So the intersection of two languages is simply, remember, languages are sets. Sets are not necessarily languages. Like the integers is a set, but it's not a language. It's a bunch of numbers. It's not a bunch of strings. So the intersection of two languages is simply the set intersection of these two sets that are these two languages. Just like in a Venn diagram, the intersection is everything they have in common, everything that's in one and in the other, both. Question? No, because the original machine doesn't accept only things in the intersection, it accepts other things too that are not in the intersection. So that's a very good question. It's a very subtle question. He's saying, why do you need this big construction? Why can't you just take the original machine that accepts stuff in the intersection? Because it also accepts stuff that's not in the intersection. No, it matters when it's finite too. So let's beat on this point. Give me an example. So if I wanted a program that prints out all prime numbers, so write a program that prints out all prime numbers. How many can imagine how to do this? Really? Only 2 people? All right, let me ask again. You write a program in C or Java or C++, whatever language you want, that prints out, keeps printing out all prime numbers. The longer you run it, the more prime numbers it prints, and eventually it prints out every single prime. Eventually. So I'm not saying it'll ever terminate, but for every prime, no matter what, eventually it'll be printed out. How many can see how to do that in Java or C? Good, that's better. How many lines of code are we talking about? Roughly. How many lines of code here? 10, 100, 1,000? Just about 10 lines, right? A dozen lines, most. All right, let me give you my program for this. My program to print out all prime numbers. While I goes from 1 forever, print I. 2 lines. Again, the 2 lines of my program is, while I goes from 1 on up forever, print I. How many agree that my program will print out all prime numbers? Of course it will. Gotcha. 2 lines. You took 10, I took 2. What happened here? What's the problem with my program? Yeah. Yeah. The point is this. Your program needs to do what it should, but it must not do what it should not do. That's very important. Not only should it print out what is specified for it, it should not print out anything else. I never said that explicitly. I just said it must print out all prime numbers. I never said it must print out only prime numbers. So gotcha. And the reason I'm harping on this example is because the question he raised just a few minutes ago, very astute question, he said, why can't you use the first machine? Well, the first machine accepts the intersection. Great. But it also accepts stuff that's not in the intersection. Too bad. It's like the prime number program prints out composite numbers as well as primes. That's not what you want. That's no big trick. So when you write a program, maybe you never thought of this explicitly, but it must do what is specified, but it must not do what is not specified. That's just as important. You can't just throw in extra stuff for it to do, because that trivializes everything. Okay, very subtle point, but very important point. And that's why we need to very carefully accept what's in the intersection, but not anything else. Otherwise, it's not the intersection, it's the intersection plus stuff, and it's something else. It's not the intersection anymore. Just like those, my program prints out primes is not just the primes. It's the primes and the composites. In fact, it's all the integers. And that's kind of off kilter. That's not what was intended. It doesn't accomplish much. Okay, any other questions about this before we move on to deeper things? So if I say the union preserves regularity, now it should be easy. What's the proof that the union preserves regularity? There's 2 ways to do it. One is to use a proof like we just did here, but instead of just having this double red state be final, you can have these other states that have just a single red state and it be final too, because it's either or is still okay for the union. For the intersection, it must be both. A intersection is an and, right? A union is an or. But here's a much easier way to do it. Use De Morgan's law. So De Morgan's law says that the union of two sets is simply the intersection of the complements, and you complement that. So the union, in terms of De Morgan's law, is the complement of the intersection of the complements. How many get that? In logic notation, it's very similar, right? The or is the knot of the end of the knots. And conversely, the and is the knot of the or of the knots, De Morgan's law. So there's a direct analogy to sets, because sets are defined as and or in terms of intersection and union, respectively, right? But why am I doing it this way? Because we already know that complementation of a regular language preserves regularity. If you take the complement of a regular language, you get a regular language back. What's the proof of that in one sentence? Take a regular language, complement that language, you get a regular language yet again. Not the same language, a different language, but it's still regular. Remember the proof from 3 or 4 slides ago? It wasn't that long ago. It's worth looking at. Complementation preserves regularity. What was that proof in a sentence? Why does that work? Yeah. Yeah, you do the exact opposite by negating final, non-final states. So you're basically simulating what it does and then flipping the answer. Yes to no and no to yes. So that accepts the complement, which means the complement is regular too if the original was regular. Take the finite automata for the original, flip it around, final and non-final states. Now you got the complement. Question? Yeah, the initial state is still the same. You just flip final and non-final states. Very important. Yeah, you don't do anything with the initial state. Because you want to do a straight-out simulation of the original, so wherever the original starts, you want to start too, in a complement machine. You don't want to start somewhere else. Very important. All right, so complementation preserves regularity. And we just proved that intersection preserves regularity too. And now we got the Morgan's law. The Morgan's law says that the union is just a function of the complement and an intersection. So complementation preserves regularity, intersection preserves regularity, and because union is simply represented as a function of intersections and complements in some combination, and both of these operators preserve regularity, it preserves regularity, it being the union. How many get that proof? So it's even simpler than previous proof. We don't have to write this long cross-product machine and look at pairs of states and be careful what the transition function becomes among superstates, on and on and on. Of course, you can still do that. And here it is by doing it. So that's a second proof. So the first proof was a one-liner, the Morgan's law. So you see how now you have certain closure properties, other closure properties fall right out of it. They now become easy. Or you can do it the hard way. You can say, use the cross-product construction, use power set, the cross-product construction, and have pairs of states and the super transition function and so on and so on, except that not just mark final as if both are final, but mark as final superstates if one is final or the other is final or both are final, because you're doing the or, not the and, because you're going after union, not intersection. How many understand both proofs? Good. One is short, one is not so short. So remember, beginning of the course, we said try to find elegant ways of proving things. The first proof is elegant, because it's just one application of the Morgan's law. There's no place for truth to hide. It's so short. It's so simple. The second one is complicated, and it uses the cross-product construction. You have to spell it out. The final state set is the cross of finals and non-finals, or non-finals and finals, because you pick up all cases and blah, blah, blah. Okay, that works too. It's just longer and more convoluted. But we already done it once, so now you can do it again. How about set difference? The difference of two languages, if both are regular, is also regular. So the difference of two regular languages is regular. In other words, the difference operator preserves regularity. Why is that true? Try to come up with a short proof, not a long one. All right. Here it is. So the difference of two languages is simply the first language intersected with the complement of the other one. And it's just not, this is not an identity about languages, it's an identity about arbitrary sets. If you want to take the difference of two sets, it's everything that's in the first, but not in the second. Because if it's in the second, it'll be subtracted from the first, and it ain't going to be there in the difference. So how many get this identity with respect to two sets? Now, languages are sets in particular. So if it's true about sets in general, certainly it's true about languages, which are a special kind of set. It can't be helped, right? The general holds true to the specific. The specific doesn't necessarily hold true for the general. So once you know that, and you know that intersection preserves regularity, and complementation preserves regularity. So if L2 is regular, so is its complement. And if L2 complement is regular and L1 is regular, so is their intersection by the previous theorem from the previous slide. And therefore, because they're equal to L1 minus L2, so is their difference regular, because equal things have equal properties. So if something is an integer and it's equal to something else, you can be sure that that something else is also an integer, regardless of what else it is. How many get that? Equal things have equal types. So these two things are equal because the right-hand side is regular by preservation of regularity properties of intersection and complementarity. And because it's equal to the left-hand side, and the left-hand side is the difference is regular too. Because they're equal, because this is a set identity. So one-line proof, elegant. Or you can use the cross-product construction. In the cross-product construction, make sure that the first one accepts and the second one rejects, right? So take all the accept states of the first one, cross them with all the non-accept states of the second one, and those become the final superstates in your cross-product construction, and that works too. It's just longer and more convoluted and harder to follow. How many get that? Good. Now you're getting the hang of it. So what if I say XOR? The XOR operator preserves regularity. What is the XOR? The XOR of two sets is everything that's in one or the other, but not in both. In other words, it's the union minus the intersection of two sets. That's the XOR of two sets. Just like in logic, if you have true XOR true, that's no good. That's false. Because XOR means one has to be true, the other must be false, or vice versa. If they're both false or both true, the XOR is false. So the XOR of two languages must be in one language, must be in the union, but not in the intersection of the two languages. So now we have closure properties from before. You can see that the intersection preserves regularity from before. The union preserves regularity from up here. The difference preserves regularity from over here. So you got three operators, union, intersection, and difference, all three of which preserve regularity. So their combination preserves regularity also, necessarily, because it's equal to the XOR on the other side. So equal things have equal types. The right-hand side is regular, and therefore the left-hand side is regular too. QED, end of proof. So now proofs become easy. Once you have a few closure properties nailed down, you can combine them in all sorts of ways to get yet more closure properties for pretty cheap, right? And if you want to see the full notation, you know, is the final state set in the super machine, if you do the cross product way, will be that, basically. So identity-based proofs are easier than hardcore from first principle kind of elementary proofs. But you got to do some of the latter to get easy access to some of the former. And next time we're going to start with non-determinism, but let me just tell you what it is. It's when the computation basically starts bifurcating. And so the next state is no longer unique. You can have several next states, right? It's like the science fiction stories where time splits up, you know, parallel universes, and they begin to diverge and evolve independently of one another. So the computation is no longer a list of states, a sequence of states. It's a tree of states. And then you may wonder, if the computation is a tree of states, how is acceptance defined? And it's defined as if any one of the branches of the tree ends up in a good place, an accepting place, the whole computation is said to be accepting. And so next time we'll start with that. Any questions about anything we did today? So now we're going deeper into finite automata, soon into regular expressions, and we'll take it up next time.
I don't know where it is right now.